After studying this module, you should be able to know about metal-metal bond, learn different types of metal-metal bonds, study examples of metal complexes having metal-metal single or multiple bonds, analyze spectroscopically evidences for the presence of metal-metal bond. The metal-metal bond is a bond between two metal centers, particularly between two transition metal atoms, which ranges from a single to a quadruple bond. The existence of metal-metal bond is mainly because of the presence of n plus 1s, n plus 1p and nd orbitals as valence shell electronic configuration. The transition metals can form three general types of bonds such as covalent bond, dative bond and weak metal-metal symmetry interactions, where the covalent bonds being the strongest and the symmetry interactions are the weakest. The compounds containing a large number of metal-metal bonds forming triangular and larger structures are called cluster compounds. However, these also include linear-linear metal-metal bonds. The metal clusters can also be defined as any entity that contain a metal-metal bond. The journey started with the identification of mercury-mercury bond in the mercurous ion in Hg2Cl2, which was the first D block metal-metal bonded species. Most of these cluster compounds are homometallic. However, there are exceptions with heterometallic cluster complexes. Some examples of clusters are shown here. Let's study the classification of metal clusters. Metal clusters have been classified in two major categories. Number one, the polynuclear carbonyl, nitrosyl and related clusters can be categorized as class 1. These clusters are mainly formed by metals in lower oxidation states, that is -1 or +1, which include the metal ions residing on the right hand side of the periodic table. The other category, class 2, includes clusters formed as halides and oxides of transition metal complexes in their higher oxidation states. The transition metals lying on the left hand side of the periodic table, that is second or third row transition metals, form such type of cluster compounds. For example, the Re2Cl8 2- cluster contains a rhenium-rhenium single bond with +3 oxidation state on each rhenium center in the cluster. Criteria for metal cluster formation. There is general trend that transition metals having large energies of atomization, that is zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, hafnium, tantalum, tungsten, rhenium, osmium, iridium and platinum display higher tendency to form metal clusters. Nature of the d orbital. The effective nuclear charge is inversely related to the size of the d orbital. The higher nuclear charge tends to reduce the effective overlap of the d orbitals, which is unfavorable for cluster formation. For example, the first row transition metals with higher oxidation states, that is +2 or +3, do not offer sufficient orbital overlap and therefore poses an unfavorable situation towards cluster formation. Let's study about the metal-metal bonding in metal clusters. There are three major types of bondings in the metal cluster. The first one is covalent bonding. One electron from each metal atom constitutes a single metal-metal bond between the two metal atoms. This is the most common type of metal-metal bond, ranging from a single to a quadruple metal bond. Molecular orbital theory can be used to explain the overlap of various orbitals to form three types of bonds, namely a sigma bond, pi bond, and the recently introduced delta bond or the quadruple bond. Considering the possible overlap between the d orbitals and adjacent metal atoms, one can figure out that a sigma bond between two metal atoms is a result of overlap of dz square orbital from each atom. The two pi bonds can be formed by the overlap of the dzx and dyz orbitals. The two delta bonds can arise from the two face-to-face overlap of dxy and dx square minus y square orbitals. The dx square minus the y square orbital is also utilized for bonding with ligands. The energy diagram shown here points towards the possibility of a quadruple bond which could result when all the bonding orbitals are occupied to give an electronic configuration of sigma square pi 4 delta 4. Examples of multiple bonds containing metal clusters are here. As the number of electrons increases, the possibility of the formation of higher number of bonds between two metal atoms increases. If the number of d electron involved goes beyond 8, the electrons go to the antibonding orbitals and hence the number of bonds tends to decrease. In a case where metal atoms have d8 or d10 electronic configuration are involved, there is practically no chance of bond formation between the two metal atoms due to the filling of antibonding orbitals. We can study from this table that electron count for d1d1, the resulting bond metal-metal bond is a single bond. For d2d2 electron count, the resulting metal-metal bond is double bond. For d3d3, the resulting metal bond is triple bond. d4d4, it is a quadruple bond, which is the optimum situation. d5d5 electron count will involve a triple bond. d6d6 will involve a double bond, and the d7d7 will involve a single bond, and absolutely there is no bond formation for d8 and d8. Now we will study how we can calculate the bond order. For example, for bond order 3, you can see in this that there are total number of electrons are 6, where 6 electrons are distributed in 2 sigma orbitals and 4 in pi bonds, and there is absolutely no electron in the antibonding orbital. With the result, the bond order will be 6 minus 0 divided by 2, that will come out to be 3. For bond order 3.5, you can see total number of electrons are 7. So 7 minus 0, 0 means there is no electron in the antibonding orbital. So 7 minus 0 divided by 2 will come out to be 3.5. In the next one, you can see that the total number of electrons in the bonding orbitals are 8, and there is no electron in the antibonding orbital. With the result, the bond order 4 is 8 minus 0 divided by 2. Let's study about the dative bond. This bond is formed when one metal having filled d orbitals coordinate to a metal atom containing an empty d orbital by the donation of a lone pair of electron. Dative bonds are represented by an arrow instead of a line, starting from the donor metal atom to the pointing to the unsaturated metal atom. The bimetallic nickel complex has one dative bond as shown in this example. Donor nickel has a D10 electronic configuration, whereas the acceptor nickel atom has D8 nickel 2 electronic configuration. Weak metal-metal symmetry interactions. The weak metal-metal symmetry interactions are as a result of symmetrical overlap of molecular orbital. This overlap is generally between filled and empty metal-metal bonding and or anti-bonding orbitals. These interactions are typically seen in few bi or polymetallic D8 complexes both in solution and in the solid state. For example, the iridium tetrakis isocyanide complex form oligomeric chain through metal-metal interacted stacks in solution and in the solid state without showing any evidence of a metal-metal covalent bond. These interactions were initially studied by Harry Gray, who proposed that these interactions are caused by a molecular orbital symmetry interaction between the filled orbitals and empty anti-bonding molecular orbitals. Let's study the types of metal-metal clusters. The dinuclear clusters. The first dinuclear cluster studied in detail was the species Re2X8 with 2- charge. The structural features were studied by Professor F.A. Cotton. Surprisingly, the RE-RE bond distance was found to be 224 picometers, which is very less than the average RE-RE distance, which is 275 picometers in the RE metal. Secondly, the distance between the chlorine atom is nearly 330 picometer, which is less than the sum of their van der Waals radii, which comes out to be 340 to 360 picometers. Cotton introduced the concept of a quadruple bond between the two rhenium centers. The chlorine atoms are connected to the rhenium ion in a square planar array. These are arranged in staggered configuration, forming a square antiprism rather than a cube. Few other examples which involve metal-metal multiple bonded clusters are the Hexa, Alexo, dinuclear, tungsten and molybdenum complexes with the formula M2OR6, where M is molybdenum and tungsten. Next type of cluster is trinuclear cluster. Among all the best studied examples of trinuclear clusters are those of Re, such as rhenium trihalide, the formula ReCl3 whole 3 and their derivatives, as you can see in this figure. Each rhenium atom is bonded with the other two rhenium atoms by a metal-metal single bond. They are also bonded indirectly to 3 bridging chlorine atoms, where each rhenium ion is also bonded with 2 chloride ions above and below rhenium triangular planes. The rhenium atom forms a triangle. The rhenium 3 ions have a D4 configuration. If rhenium ions are bonded with Re-Re single bond, only the complex would have been a paramagnetic complex. However, the complex is diamagnetic, which implies that the rhenium ions are doubly bonded. Next is tetranuclear cluster. A number of tetranuclear clusters are known in the literature, where most of them exist as halides and oxides of tungsten and molybdenum metals. The next class is hexanuclear cluster. Metal clusters containing 6 metal atoms have been known for many years. Mostly consist of molybdenum, niobium and tantalum atoms. Considering the case of metal chlorides, the first type of hexanuclear cluster consists of an octahedron of 6 metal atoms surrounded by 8 chloride ions, one on each face of the octahedron. In this way, the chloride ions are forming a cube around the metal octahedron. For example, such kind of arrangement can be seen in molybdenum dichloride with the formula MO6C12, which can also be formulated as MO6Cla with Cl4 outside the bracket. In this case, each molybdenum 2 ion is sharing 4 single bonds with 4 other molybdenum 2 ions and also receive 4 dative bonds from 4 chloride ions. In the second type, 12 halide ions are surrounding the molybdenum octahedron and placed along the edges. Such type of clusters are formed by niobium and tantalum. Unlike the bonding situation in hexanuclear metal clusters discussed above, each metal ion is surrounded by a distorted square prism of 4 metals and 4 chloride ions. These compounds are electron deficient. Let's summarize what we have studied. Multimetallic metal complexes possessing metal-metal bonds are called cluster compounds. They are of variety of geometries such as linear metal-metal bonds, triangular and larger. There can be homometallic as well as heterometallic metal-metal bonds. The metal cluster can be classified on the basis of oxidation state of metal ion and the bonded ligands. For example, the metal clusters containing halides or oxides as ligands are generally formed by metals in higher oxidation states. Metals clusters display mainly 3 types of bonds, namely covalent, dative and weak metal-metal symmetry interactions. Among these, covalent bond is the most prevalent one. Metal clusters display single to quadruple metal-metal bonds where molecular orbital diagrams can be used to explain the properties of a particular type of bond. The various types of metal clusters are dinuclear, trinuclear, tetranuclear and hexanuclear clusters.